Hi everybody, today's lesson is on solving radical equations. Now this is a topic that you've done in several math classes before, Algebra 1 and Algebra 2 for example. So I'm going to run through some examples of things that are familiar, and then towards the end we'll get to some new stuff. Now I didn't have a clean copy of this, so I'm just going to show you my key and explain the steps as we go. So what we'd like to first do for any radical equation is try to isolate the radical. So step one would be to get the radical alone. So I'm going to add 8 to both sides. And then in order to get rid of the radical, I'm going to square both sides. Okay, so when you square both sides, the square and square root knock each other out. So I'm left with 4 minus 3x here. And here you'd have to write x plus 8 twice and then FOIL, multiply, distribute in order to get this trinomial here. Bring everything to one side of the equation and factor. The last step of all radical equation problems is to check to make sure the answer works, because sometimes you can get what's called an extraneous root, an answer that you got by doing a valid step, say -4 and -15. You did all the steps correctly here, but -15 will not work in the original equation when you plug it back in. So you can see here's my check. It's using the original equation. That's what's typed out, given on a test in your book for your homework tonight. And you can see again, it worked for -4, but not for -15. So we just don't include that in our solution set. Let's go ahead and take another look at a different example. Again, as always, feel free to stop and rewind as you feel needed. So in this problem over here, we have a cube root and not a square root, which is no problem. In order to start off this, I want to isolate the radicals. Well, this is as isolated as they can get. There's one on each side. So the next thing I'm going to do is I'm going to cube both sides. You're always raising both sides of the equation to the index value. The index is the number that sits in the cup over here. So for a square root, it's 2, even though we don't write a 2 there. So if I cube both sides, that gets rid of the cube roots on both sides here. Bring everything to one side of the equation and factor. Whenever you see an x squared, remember that you'd like to try to keep it positive, because it's much easier for us and much more common for us to factor when the x squared term is positive. So I did that and I factored. I checked in with the original equations. They both work. So I listed them in my solution set, least to greatest. The next one gets a little bit more dicey, I guess you could say. So in this original problem here, and by the way, you see number 12 here. On the first example, it said page 307. That's where I'm getting the examples that I'm using from the textbook. So in an instance like this where there's two radicals on one side of the equation, the best you can do is isolate it in the best way you can. So I'm going to bring one of these to the other side. So I'm going to bring this radical over here. So when I do that, then I can square both sides. So if I square both sides here, square and square root knock each other out, so you're left with 3x plus 4. And over here, when you have a binomial squared, whether it's something that looks like this, or if it's like the previous page when you had x plus 8 squared, you've got to write it twice and multiply it out. So let me just show you this multiplication here, because I know this might look a little bit tricky. So first terms, 2 times 2 is 4, that's easy. Outer terms, 2 times radical, 2x minus 4 is just that. Inner terms, 2 times this radical is just that. And in the last terms, this radical times this one, when you multiply a radical by itself, you could get essentially radical 2x minus 4 squared. Well, what would happen? The square and square root would cross out, and so you're just left with, here, let me put this over here. You're left with just 2x minus 4, okay? And that's because a radical times itself would lend itself to being squared, and then they would cancel out. So then I combine like terms. When you add these radicals here, these middle ones, remember you add coefficients to be 4, and then you keep the radical the same. That's just how you multiply radicals. You add up the coefficients, and if the radicands are like, that's what's under the radical, then you just keep it there. So this is what I ended up getting over here, 4 radical 2x minus 4 plus 2x, so that's what this simplifies down to on the right side. And now when I do that, I get myself into another situation where I have another radical to contend with. So I'm going to do this, basically start over. I'm going to try to isolate this radical now. So I subtracted the 2x over. And then you can actually divide both sides by 4 if you'd like. It makes it a little bit ugly to work with. So I'm going to keep it here. So I know that radical is not totally isolated. But for this purpose, when I square it, it's going to be pretty easy to do. So when I square this left side, again, you just multiply by writing x plus 4 twice, foiling it out. In here, 4 squared is 16, and the square root squared would cancel out to just be 2x minus 4. And from here, bring everything to the left side, and I'm able to factor by easy trinomial. I get 2 possible answers. Remember when you check to put them back into your original equation, okay? If you put them in a different equation like this one or this one down here, you can get a false check. So here these both work, so I put them both in my solution set from least to greatest. A check, by the way, yes, it's required for the step, but you don't have to show your work. If you do the check in your head for a problem, that's fine too, as long as your final answer reflects what the answer should be. Okay, now number 22 might seem like, where did this problem come from? I thought we were doing radical equations. Well, remember, when you have a rational exponent, remember the word rational should signal the word fraction in your brain. So when I hear the word rational exponents, I'm thinking fractional exponents. Remember, if you have a fraction as an exponent, the numerator is the power, the denominator is the root. So this can also be rewritten as x to the power of 3 and the root is 2. X to the power of 3 and the root is 2. So what I call these problems are radical problems in disguise. And you treat them the same way. You want to isolate the radical, or in this case, you want to isolate the rational exponent, the x to the power of 3 halves. Subtract 5, divide by 4. And then when you go to isolate the x at this point, the way I get the x alone on the side is I raise both sides to the reciprocal of this power 3 halves. The reciprocal is 2/3. And the reason why that works is because if I multiply an exponent to another exponent, I'd multiply. And if I multiply these two, I would get 6 over 6, which is just 1, or just x. Here, it's x to the power of 2 and the root is 3. So x to the power of 2 is 16. The cube root of 16, I'm just going to leave it that way because it's not an exact number. That is my final answer here. When I plugged it into this problem, the original, it checks out. So in the next problem, now this is going to be something kind of new to you guys. In the next problem, look at this over here. Yes, this is a radical equation problem, but unlike the other one, I can't just isolate the power over here. And I can't add these two x's together because they're not like terms. So we're going to use a process called U substitution. This is something you'll do a lot in calculus. Maybe I shouldn't even say a lot, but you'll definitely do it in calculus for a variety of problems. When we do what we call a U substitution, and the letter U is arbitrary, you could use whatever letter you'd like, but you'll definitely hear the phrase U substitution in calc, so I want to go with that. Using a U substitution takes a hard problem and makes it look easier. So in this problem over here, if I let U be x to the power of 1/3, okay? So wherever I see x to the power of 1/3, I make it a U. That's easy over here because it's just x to the 1/3, make it a U. But over here, if I have x to the power of 1/3, I can make it into x to the power of 2/3 by raising it to the power of 2. So this is U squared. U squared. This is the same thing as x to the power of 2/3 because U is x to the power of 1/3, and then I've got my square there. And if I multiply an exponent to an exponent, I would get x to the power of 2/3. So this problem right here, given that U is x to the power of 1/3, is the same as the one above. Now for the problems that we're doing, a little shortcut here, if you just look to the middle term, this one over here will tell you what your u substitution should be. Okay, and this will make it into a nice quadratic for us. So now I'm going to solve this problem with the u, and then later on I'll put back the x to the power of 1/3. So if I factor this easier equation, I get this. I get 2 possible answers for u. So now at this point, get rid of the u and make it x to the power of 1/3 again, okay, for both answers. So instead of u equals -2, replace the u with x to the power of 1/3 equals -2. And so when looking at this problem over here then, if I raise both sides to the power of 3, just to get rid of the 1/3 to get x alone, I will get -343 here. And I'm looking over here, this should be outside. Excuse my little error there. This should be outside. -2 to the power of 3 is -8. And so when you go to check these, you can make your life simple and just use your calculator. Like just do -343 to the power of 2/3 plus 9 times -343 to the power of 1/3 plus 14. Make sure it equals 0. Okay. So let me show you another one of those, because again, those are the new thing really. That can be a little bit tricky. So here's another problem where I would use a u substitution here. And again, the reason why is when looking over here, this is not something I can easily solve for. But if I just subtract over the 3, if I just take this middle term here and let that be u, okay? So this substitution makes obvious sense here because that's just a u. And then this would become 2 times u squared, because if I took x to the power of -1 and squared it, multiply, this would be x to the power of -2, which is what this is. So this is a much easier problem for us to work with. You can factor here by hard trinomial, and you get 2u minus 3 and u plus 1. Solve here for u, and then once you've solved for u, that is when you replace the u with our substitution, in this case x to the power of -1. So I've solved for u here and here. I'm going to replace it now with x to the power of -1. Now when you raise both sides, it might look weird, like why am I raising it to the power of -1? Because if I multiply -1 times -1, it makes +1. Also, you can think of it as raising it to the reciprocal power. The reciprocal of -1 is still -1. So that's why I'm raising it to the power of -1. So if I do that, this makes x. When you raise something to a negative exponent, in order to get rid of the negative exponent, you flip it. So whatever is being raised to the negative exponent gets flipped. So 3/2 flips to 2/3, and that's what makes the power now +1. I don't need to put that there because the power of +1 is just not necessary. But I say that because if this were like to the power of -2, you'd have to flip it and then square both parts. And in this last part here, -1 to the power of -1. Again, to get rid of this -1 here, you would have to flip what it's being raised to, but when you flip -1, it's still -1. And again, you do need to check, make sure you check in the original equations, always. And again, for ones like this, let your calculator do the hard work, okay? Just make sure that when you're plugging this in your calculator, you've got like, 2 times, make sure you use parentheses, -1 to the power of -2, like that, okay? Because if you don't use parentheses, then you're not going to get it to equal 3, for example. So that's it for this lesson over here. Make sure you're doing the homework as stated in the classroom guide that I posted on Google Classroom. Have a good night.